How does consciousness happen? And why is life in the first person? The modern incarnation of this problem is usually traced to Descartes, who in the 17th century distinguished between matter stuff, res extensa, the stuff that these desks are made of, that clothes are made of, but also that brains and bodies are made of, material stuff, and res cogitans, the stuff of thought, of feelings, the stuff of consciousness. And in making this distinction, he gave rise to the now infamous mind-body problem, and life has never been simple ever since. But Descartes actually generated even more mischief with his doctrine of the beast machine, which I'm going to mention now because it anticipates where I'm going to end up as the bell rings when I finish in an hour. Before Descartes, people commonly believed in something called the great chain of being, with rocks and plants at one end, and other non-human animals a bit higher up, then humans, and then angels and gods at the very top. And this great scale of being was also a scale of moral virtue, so that humans had more moral virtues than animals, than plants, and then rocks, and so on. Now, Descartes, in making this division between mind and matter, argued that only humans had minds, and therefore moral status, while other animals didn't have minds. They were merely physiological machines or beast machines, morally equivalent to plants and to rocks. And in this view, the physiological mechanisms that give rise to the property of being alive were not relevant to the presence of mind or consciousness. And I'm going to propose, at the end of this talk, the opposite, that our conscious sense of self arises because of and not in spite of the fact that we too are beast machines. So to get there, let's return to the apparent mystery of consciousness. What's extraordinary about the brain is not so much the number of neurons, though there are about 90 billion. It's not even the number of connections, though there are so many that if you counted one every second, it would take you about 3 million years to finish counting. What's truly extraordinary are the patterns of connectivity, which to a large extent are still not known, but within which are inscribed everything that makes you, you. The challenge is then this, at least the way I see it. How can the structure and dynamics of the brain, in connection with the body and the environment, account for the subjective phenomenological properties of consciousness? And considering things this way, we come up against what the philosopher David Chalmers has often called the hard problem of consciousness. And the idea is this: there is an easy problem. The easy problem is to understand how the combined operations of the brain and the body give rise to perception, to cognition, to thinking, to learning, to behavior, how the brain works, in other words. The hard problem is to understand why and how any of this should have anything to do with consciousness at all. Why aren't we just robots or philosophical zombies without any inner universe? Now, there's a tempting intuition here, which is that even if we solve the hard problem, even if we solve the easy problem, the hard problem would still remain as mysterious as it seems now. But this just seems wrong-headed to me. It may not be necessary to explain why consciousness exists at all in order to make progress in understanding its material basis. And this, for me, is the real problem of consciousness. How to account for its various properties in terms of biological mechanisms without pretending that it doesn't exist at all, as you do if you solve the easy problem, and without trying to account for why it's part of the universe in the first place, which is sort of the hard problem. And in the history of science, we've been somewhere similar before. It's hard to say if it's exactly the same situation. But in our understanding of life, eminent biochemists of the time found it entirely mysterious how biological mechanisms could give rise to the property of being alive. And there were proposals of things like élan vital and essence vitale and all sorts of other stuff. And although we don't yet understand everything about life, this initial sense of mystery about life has to a large extent dissolved as biologists have just got on with the business of understanding the properties of living systems in terms of mechanisms. An important part of this story was the realization that life is not just one thing, but rather a constellation of partially dependent and partially separable processes, like metabolism, homeostasis, reproduction. In the same way, to make progress on the real problem of consciousness, it can be useful to distinguish different aspects or dimensions of what it is to be conscious. The space of possible minds, if you like. And one simple classification is into conscious level, which is the property of being conscious at all. For example, the difference between being in a dreamless sleep or under general anesthesia, and being awake and conscious as you are now. Conscious content, when you are conscious, you're conscious of something. The myriad sights, sounds, smells, emotions, feelings, and beliefs that populate your inner universe at any one time. And one thing you're conscious of when you are conscious is the experience, the specific experience of being you. And this is conscious self. So what's important about this way of looking at things is that it's grounded in a theory that tries to explain why certain sorts of brain dynamics go along with being conscious. And put very simply, the idea is this, and it goes back to Giulio Tononi and Gerald Edelman, people that I went to work with in America about 18 years ago. The idea is very simple. Consciousness is extremely informative. Every conscious experience you have, or have had, or will have, is different from every other conscious experience you have had, are having, or will have. Even the experience of pure darkness rules out a vast repertoire of alternative possible experiences that you could have, or might have in the future. There's a huge amount of information for the organism in any conscious experience. At the same time, every experience that you have is highly integrated. Every conscious scene is experienced as all of a piece, as bound together. We don't experience colors and shapes separately in any way. So conscious experiences at the level of phenomenology combine these properties. They are, on the one hand, highly informative, composed of many different parts. On the other, bound together in a unified whole. If you're trying to naturalize a phenomenon which seems mysterious, the ability to measure it is usually one of the most important steps you can take. And consciousness, conscious level, depends on a complex balance of differentiation and integration in brain dynamics, reflecting the fact that conscious experiences themselves are both highly informative and always integrated. Now, when we are conscious of something. So what are the brain mechanisms that determine the content of consciousness? And the hero for this part of the story is the German physicist and physiologist Hermann von Helmholtz. And he proposed the idea that the brain is a kind of prediction machine, that what we see, hear, and feel are nothing other than the brain's best guess about the causes of sensory inputs. And the basic idea is, again, quite simple. The brain is locked inside its bony skull. It has very indirect access to the external world. All it receives are ambiguous and noisy sensory signals, which are highly indirectly related to this external world of objects and so on, if there is an external world of objects out there at all. Don't know about that. Perception in this view is by necessity a process of inference, in which the brain interprets these ambiguous and noisy sensory signals with respect to some prior expectations or beliefs about the way the world is. And this forms the brain's best guess of the causes of the sensory signals that are impacting our sensory surfaces all the time. What we see is the brain's best guess of what's out there. And I want to give you a couple of examples that illustrate this process. It's quite easy to do in a way. This first example is a well-known visual illusion called Adelson's checkerboard. Now here, you'll see two patches. You'll see patches A and B. And I hope to you they look to be different shades of grey. Do they? Yeah, they look to be different shades of grey. Of course, they are exactly the same shade of grey. I can illustrate that by putting an alternative image and joining up those two patches. You'll see that it's the same shade of grey. You may not believe me, so what I'll do is I'll shift it along and you'll see even more clearly. There are no sharp edges. It's the same shade of grey. What's going on here, of course, is that the brain is unconsciously applying its prior knowledge that a cast shadow dims the appearance of surfaces that it casts onto. So we therefore see the patch B as being lighter than it really is in order to account for that effect. And this is, of course, an illustration of the success of the visual system, not its failure. The visual system is a very bad physical light meter, but that's not what it's supposed to do. It's supposed to, or one thing it's supposed to do, is to interpret the causes of sensory signals in terms of meaningful objects in the world. It's also an example of what we sometimes call cognitive impenetrability. Even if you know the patches are the same shade of grey, when I take that bar away, they again look different. So, can't do much about that. The second example just shows you how quickly the brain can take in new prior information to change the nature of conscious perception. This is a so-called Mooney image. And if you haven't seen it before, hopefully what you will see here It's just a pattern of black and white splodges. Does everybody kind of get that? Black and white splodges? Yeah, some of you might have seen this before. And now what I'm going to do is fill it in, and you'll see something very different. What you'll see is a very meaningful scene here involving at least two objects, a woman, a hat, and a horse. Now, if you stare at this for a while, I won't leave it up for too long, but if you just look at it for a little bit, and then I take that image away again, you should still be able to see the objects within that image. Now, for me, this is quite remarkable because the sensory information hasn't changed at all. All that's changed are your brain's prior expectations about what that sensory data signifies, and this changes what you consciously see. Now, this also works in the auditory domain. Here are two spectrograms. This is something called sine wave speech, and what you see here are two time-frequency representations of speech sounds. The one on the top has all the sharp acoustical features that pervade normal speech removed, a little bit like thresholding an image. And the bottom is something else. So I'm going to play you the top first, and let's see what it sounds like.
Jazz and swing bands like fast music. Jazz and swing bands like fast music.
And now I'll play you something else.
Jazz and swing fans like fast music.
So I hope you all understood that piece of sage advice. And now if I play the original sound again.
Jazz and swing bands like fast music.
Yeah? So it's exactly the same. Again, all that's changed is what we expect that sound to signify. One more time, just for luck.
Like fast music.
It's not just a bunch of noisy whistles, it's speech. Now, this typical framework for thinking about these kinds of effects is Bayesian inference. And this is a form of probabilistic reasoning, which is applicable in all sorts of domains, not just in neuroscience, in medical diagnosis, all sorts of things, finding lost submarines. But in neuroscience, we talk about the Bayesian brain, and it's a way of formalizing Helmholtz's idea that perception is a form of best guessing. And the idea is that sensory signals and prior beliefs can be represented as probability distributions. So, for instance, this yellow curve is the probability of something being the case, maybe that you've got a brief glimpse of an object moving to the right. The sensory data may say something different. It may have a probability that peaks at a different angle of movement. Maybe it's drifting in a different direction. And the optimal combination of the prior and the likelihood, the yellow curve and the red curve, is this green curve, which we would call the posterior distribution. And that represents the best optimal combination of these two sorts of evidence. And the idea is, well, that's what we perceive. Thinking about perception in this way does something rather strange to the way classically in neuroscience people have thought about perception. The classical view is that the brain processes sensory information in a bottom-up or feed-forward direction. So this is a picture of the visual system of the monkey, and the idea is that information comes in through the retina, it then goes through the thalamus, it then goes to the back of the brain, and as the sensory signals percolate deeper and deeper and deeper into the brain, they encode or represent progressively more sophisticated features of objects. So you start out at early levels of visual cortex with response to luminance and edges, and then higher up to objects, including other monkeys. What's important here is that the perceptual heavy lifting is done by information flowing in this bottom-up or feed-forward direction. Now, the Bayesian brain idea says something very different. It says that what's really important are the top-down or inside-out connections that flow from the center of the brain back out. And we've known for a long time there's a large number, very large number of these connections, and some descriptions more than flow the other way around. But their function has been rather mysterious. Thinking about the Bayesian brain gives us a nice way to interpret this, which is that it's exactly these top-down or inside-out connections that convey predictions from high levels of the brain to lower levels, back out to the sensory surfaces. So these blue arrows convey the brain's predictions about the causes of sensory signals. And then what flows in the feed-forward or bottom-up direction from the outside in, that's just the prediction error, the difference between what the brain expects and what it gets at each level of description. So this is often called predictive coding or predictive processing in some formal frameworks. And the idea is that minimization of prediction error then occurs across all levels of this hierarchy at the same time, and what we then perceive is the consequence of this joint minimization of prediction error. So you can think of perception as a sort of controlled hallucination in which our perceptual predictions are being reined in at all points by sensory information from the world and the body. All this stuff is all very good, but predictive processing is not a theory of consciousness. Nothing I've said has anything to do with consciousness at all. It has to do, it's a very general theory of how brains do what they do, how they do perception, how they do cognition, how they do action. So somewhat counterintuitively, I think this is exactly why it's a great theory of consciousness. And the reason I think this is because it allows us to ask all sorts of questions about the real problem, about what it is, what happens in brains that underlies what you happen to be conscious of right now, without getting sucked into the metaphysical plug hole of why you're conscious in the first place. In other words, it provides a powerful approach to looking for neural correlates of consciousness, those things in the brain that go along with being conscious, because we can now take advantage of a very general theory of how brains do what they do, rather than just looking at this region or that region. So we've been using virtual reality over the last few years to try to get at some of these ideas. This is an Oculus Rift, which is now available to buy, I think, or consume. And we've been using these to address some of these real-world aspects of visual perception. And one of these real-world aspects is called perceptual presence. And this is the observation that in normal perception, objects really seem to be there, as opposed to being images of objects. And this is, of course, what Magritte plays with in his famous painting, The Treachery of Images. For instance, this is an object, I think it's there, and in some sense I can perceive the back of it, even though I can't see the back of it, even though the back of it's not giving me any sensory data, I perceive it as an object with a back. How does one explain that? Well, one idea you can come up with within this Bayesian brain framework is that the brain is not only predicting the possible causes of the sensory signals it's getting right here, right now, but it's also predicting how sensory signals would change were I to make particular actions, were I to pick this object up and move it around, or just move my eyes from one place to another. There's a long paper I wrote about that, which don't read. Please don't read it. But that's the basic idea. And how do you test an idea like that? So we've been using some innovative virtual reality methods, or augmented reality methods, with my postdoc Kesuke Suzuki. And what we do is we have virtual objects. And these virtual objects, well, they either behave as a normal object would. They're all weird, unfamiliar objects. But they can either behave as a normal object would behave. So you can learn to predict what would happen. This one is weird. It always shows you the same face, a little bit like having the moon on a plate in front of you. And then there are other conditions where objects respond to your movements, but they do so in unreliable and strange ways. So the question is, what does the brain learn about these objects, and how do we experience them? Do we experience them as objects in different ways when they behave differently? And we're still doing those experiments. Another way we can use VR is to investigate what happens in visual hallucinations of the kind experienced in psychosis and in certain other more pharmacologically induced conditions. So this, what we're doing here is we're coupling immersive virtual reality. Imagine you've got a headset strapped to your head again, with clever image processing that models the effects of overactive priors on visual perception to generate a highly immersive experience. This is Sussex campus, actually, but now it seems quite different than it did at lunchtime today, I'll tell you that. What we've done, we've recorded this panoramic video, which we can feed back through a VR headset, and we've processed this video through one of these Google Deep Dream algorithms you might have seen that can generate sort of bowls of pasta that look like animals. And this might seem like a lot of fun. It is fun, but there is a serious purpose here, because it allows us to model the effects, model very unusual forms of perception and how they might play out in different ways in the visual hierarchy. And understanding how visual hallucinations might happen and how the wider effects they have on the mind, I think, is a very important part of studying visual perception. So that brings us to the second take-home message, which is that what we consciously see is the brain's best guess of the causes of its sensory input. Normal perception is a fantasy that is constrained by reality. Now, before I move on to the last section, I want to pay tribute to an unlikely character in the talk about neuroscience, which is Ernst Gombrich. Ernst Gombrich was one of the foremost historians of art of the 20th century. And it turns out that Gombrich's approach to understanding art had a lot in common with ideas in the Bayesian brain, and more specifically with the idea that perception is largely an act of imagination or construction on the part of the perceiver. And this is most apparent in his concept of the beholder's share, which emphasizes that the viewer brings an awful lot to the table in the act of experiencing an artwork. So he had this to say in his 1960 book, Art and Illusion. The artist gives the beholder more to do. He draws him into the magic circle of creation and allows him to experience something of the thrill of making, which had once been the privilege of the artist. And I think for me this is very powerful when looking at especially things like Impressionist art. And here, one way to think about this is that the artist has reverse engineered the whole perceptual process so that what's there are not the objects, the endpoints of perception, but rather the raw materials, the patterns of light that engage our perceptual machinery in doing its work. And for me, this might be why paintings like this are particularly powerful. Now, the final dimension of consciousness I want to talk about is conscious self, the fundamental experience of being someone like you. There are many aspects to our experience of being a conscious self. There is the bodily self, the experience of being and identifying with a particular body, a bit of the world that goes around with you in the world all the time. There's the perspectival self, the experience of seeing the world or experiencing the world from a particular first-person perspective, usually somewhere in the body, but not always. There's the volitional self, the experience of intending to do things and of making things happen in the world, of agency. And these ideas are, of course, often associated with concepts of will. Then there's the narrative self. This is where only until now we don't have to worry about the concept of I, but when we get to the narrative self, there is now an I. There is a continuity of self-experience from hour to hour, from day to day, from month to month, and from year to year that you associate a name with and a particular set of autobiographical memories. And finally, there's a social self. The way I experience being me is partly dependent on the way I perceive you as perceiving me. I'm just going to talk in the minutes that remain about the bodily self. This is something we're working on quite a lot in Sussex. The experience of identifying with and owning a particular body. And the basic idea I want to convey is, again, very simple. It's just that we should think of our experience of body ownership in the same way that we think about our experience of other things as well. That is, it's the brain's best guess of the causes of body-related signals. And the brain is always making this inference. It's making its inference about what in the world is part of the body and what is not part of the body. But it has access, in this case, to other sorts of sensory signals, not just visual signals or tactile signals, but also proprioceptive signals, the orange arrows here. These inform the brain about the body's configuration and position in space. And then also, and often overlooked, are interoceptive signals. These are signals that originate from within the body, that tell the brain about the physiological state or condition of the inside, of the internal physiological milieu. And you can think, the idea is that our experience of embodied selfhood is the brain's best guess of the causes of all these signals put together. An important part of this idea is that interoception, the sense of the body from within, should work along the same principles, the same Bayesian principles that we've been thinking about vision and audition previously. That is, our experience of the inside of our bodies is the brain's best guess of the causes of the signals that come from the inside of our bodies. So we can think of, again, top-down predictions, carrying predictions about what the bodily state is like, and bottom-up prediction errors that report the differences between what's going on and what the brain expects. So what is our experience of the inside of our bodies? Well, way back at the beginning of psychology, William James and Carl Langer proposed that emotional experience, was really about the brain's perception of changes in its physiological state. rather than perception of the outside world. So in this classic example, seeing a bear does not in itself generate the experience of fear. Rather, seeing the bear sets in train a load of physiological changes, preparatory fight and flight responses, and it's the perception of those bodily changes in the context of the bear being around that leads to our experience of fear. So the Bayesian perspective just generalizes that idea and says that emotional experience is the brain's best guess of the causes of interoceptive signals. And this fits very nicely with a lot of evidence, and this is just one study done by a Finnish group. And all they did here was they had people report where on their bodies they felt various emotions to take place. And so you feel anxiety in one part of your body, you feel fear in another, and so on. So our experience of emotion does seem to be intrinsically embodied. Now, another part of our experience of being a body is the body as a physical object in the world. And this might seem quite easy to take for granted, since our physical body is just always there. It goes around with us, it changes over the years in unfortunate ways, but it's always there. And but it would be a mistake to take our experience of body ownership for granted. And there are some classic experiments that demonstrate how malleable our experience of body ownership is. This is the famous rubber hand experiment. Probably some of you have seen this. What happens here is that a volunteer has their hand hidden under a table, and a fake hand is put on top of the table, and then both hands are simultaneously stroked with a paintbrush. And it turns out that just seeing a hand-like object where a hand might be, feeling touch, and then seeing that object being touched is enough evidence that the brain's best guess becomes that that fake hand is in fact part of my body, sort of part of my body. This is what it looks like in practice. Here you can see the fake hand, focusing on it. There's the real hand, not focusing on it, simultaneous stroking. And there are various ways you can test it. I found in doing this, it works even better on children, by the way, if you do that. That brings me to the third take-home message about self. And with apologies to Descartes, the take-home message is that I predict myself, therefore I am. So I want to go full circle and return to this Cartesian idea of the beast machine, to try to convince you that our experience of being a conscious self is intimately tied up with our beast machine nature. And to do this, I need to mention one final aspect of perceptual inference, which has a lot to do with Carl Friston, who's done a lot of work in the Bayesian brain, UCL here in London. And if we think of the brain as being in the business of minimizing prediction errors, this can be done either by updating our perceptual predictions, which is what I've been talking about so far. And this is what Helmholtz had. Or we can minimize prediction errors by making actions. We can change what we predict, or we can make an action so that our predictions come true. You can change your sensory input, or you can change what you believe about your sensory input. One point of doing this is that you can make actions then to find out more about the world that's around you. And this is what Helmholtz has in mind when he says that each movement we make, by which we alter the appearance of objects, should be thought of as an experiment designed to test whether we've understood correctly the invariant relations of the phenomena before us. Richard Gregory much later said something similar when he talked about perception as hypothesis testing. The point of this is that we make eye movements and other kinds of movements to understand what the world is like, that in fact there is a tomato there, for instance. But there's another way to think about active inference, which is that when we minimize prediction error, what we're actually doing is controlling a sensory variable. We're preventing it from changing because we're making our prediction about what it is come true. And this is the use of active inference to control or regulate something rather than to understand what the causes of that something are. And this brings to mind, I mentioned Carl Friston. He's come up with this thing called the free energy principle. And I can only nod to the vast body of work he's done here on this with the slogan, which is that organisms over the long run maintain themselves in states in which they expect to be in virtue of having good predictive models about their own internal condition. So this takes us right back to Descartes, but in a very different way. As I said right at the beginning of this lecture, for Descartes, our physiological reality was rather irrelevant to our mind, our rationality, our consciousness. This is a quote from a 1968 paper on his beast machine argument. Without minds to direct their bodily movements, animals must be regarded as unthinking, unfeeling machines that move like clockwork. Now, I think if you try to think how this idea of our predictive models controlling our internal physiological state and the resulting experiences, that perceptual content that might give rise to, you can make the opposite case. And the opposite case would be that conscious selfhood emerges because of and not in spite of the fact that we are beast machines. I think this is a deeply embodied view of consciousness and self, and it speaks to a fundamental link and continuity between what it is to be alive, what it is to have a mind, and what it is to be a conscious self. So I repeat the third take-home message. It should make even more sense now that I predict myself, therefore I am. And I am a conscious self because I'm self-fulfilling predictions about my own physiological persistence. But there is this mystery and wonder still about how the biological machinery inside our heads gives rise to the rich inner universe that makes life worth living. And despite this mystery, modern science is making progress. I hope I've given you a flavor. Even though we don't understand how consciousness happens, we can begin to understand its mechanisms. So we should not be afraid of naturalizing consciousness. It's not a bad thing to understand its basis in the material world. As so often in science, with greater understanding comes a larger sense of wonder and a greater realization that we are part of and not apart from the rest of nature.